Yeah. All right, so I think we should get started so we don't run behind schedule. So it's good to be back with the regularly planned NPAs, and what better way to start than to introduce Ejiro. So just a little bit about Ejiro. She's currently a postdoctoral research associate at BNL, working on sPHENIX at the Relativistic Heavy Ion Collider, Long Island. Ejiro received a PhD from the University of Houston in 2020 under the supervision of René Bellewy. And then from 2020 to 2022, she was a postdoc at Iowa State University with John Lejoie, who's currently a spokesperson of the EPIC collaboration. And of course, her research broadly concerns studying matter-creating particle accelerators at high energies. And she's also the co-chair of the sPHENIX Juniors Committee and has been heavily involved with the software development for sPHENIX. So please, let's welcome Ejiro.
Thanks, Fernando, for that nice introduction. So I'm going to talk about sPHENIX experiment. So this is going to be sort of a broad talk about what sPHENIX is for, where it's at now, and what we hope to accomplish with the detector. So I just sort of kind of describe my overview here. So I start off with talking about our universe. I know a lot of us are probably familiar with it, but why not? Why not talk about it? Then I talk about colliders, relativistic heavy ion colliders. I talk about our sPHENIX science mission, and then construction status and outlook. Okay, starting from the very beginning. So what do we have? We look at. So if we start here, if you look at human beings, we have cells, and within the cells, the molecules and atoms. And if you sort of trace this tree down this way, where you have nuclei and then split into two, or mesons and baryons, which are collectively called hadrons, and you look inside hadrons, you find quarks. And basically, this is a tree describing what matter is made of. So my particular physics is really concerned about quarks and basically constituents of quarks. And so if you look here at the standard model, this will be looking at this part of this standard model. So you look here at the different flavors of quarks, and they all have different masses. So starting with the light to the more heavier ones here. So we have different elementary particles, and what about the force that governs them? In particular, there are four different kinds of forces, as we all know, but this talk really will focus more on the strong force, and the underlying theory behind the strong force is quantum thermodynamics, as you might already know, and the force carrier are the gluons. Here I just say that, you know, what the central thrust of nuclear science research, I mean, from, you know, at least from the last town hall meeting, is really to try to understand the strong force slash QCD. And I say that broadly. I know that there are, you know, various regimes of QCD, but this talk really is about hot QCD, so I wouldn't talk about EIC science or anything of that nature. So here, going back in time, we know that at some point after the Big Bang, there was the creation of the Quark-Gluon Plasma, somewhere around 1 microsecond after the Big Bang. And as the plasma sort of cooled and expanded, it formed into hadrons called, well, protons and neutrons are collectively near hadrons, and then you form, you know, low mass nuclei and things of that nature. So this, if you look at it, it's a long time ago. If we want to study the Quark-Gluon Plasma, we really have to like basically recreate it. And so this is basically a photo schematic showing that now we're getting back to creating the Quark-Gluon Plasma with accelerators. Now, so the reason why we're doing that is because, well, the Quark-Gluon Plasma was created a long time ago, so we don't have access to that. I mean, there are speculations that it's the neutron stars, but rather than going to look for anything there, we'll create some at the lab. So here I go into the relativistic heavy ion colliders. So here we'll start off with the LHC. LHC has a circumference of 27 kilometers. There are four main experiments. So there is the Atlas experiment, ELISE, CMS, and LCD. And so here it just shows you some of the collision systems used, lead, and the different center of mass energies. And similarly, we have RHIC, the Relativistic Heavy Ion Collider, and its in circumference is 3.8 kilometers. The two current experiments there now is STAR and sPHENIX very soon this year. So the collision systems there, rather than lead, is gold, and there are other systems that are coincident. So here in this talk, I will talk about the sPHENIX detector. Okay, so before I go into that and talk about the sPHENIX detector, let's look into the evolution of heavy ion collision. So we start off with having the two Lorentz contracted nuclei, which are basically like pancakes. And so at some point, there's this, of course, a phase of initial energy density, which is far from equilibrium, but there is thermalization achieved at some point, and you form the QGP phase. Hadronization occurs where this is basically a creation of particles from this plasma. The particles are still, they still have some energy to them, so there are still some collisions, or elastic collisions that are still occurring. And when that stops, you get to kinetic freeze out. So basically, this is basically a list of, or so to speak, of the different stages of the evolution of the heavy ion collision. So this talk really will focus on the QGP phase, so because this is really what sPHENIX is made for, to basically build the QGP. Nonetheless, before I go into talking about the QGP, I should basically introduce some global observables that are very central to all physics. So there's something called centrality, which really is a measure of how the degree of overlap between the two colliding nuclei. So as you know, central collisions are more head-on, and peripheral collisions are basically grazing each other. And so from so here I just show you a distribution of the number of charged particles and the different, this will be basically being into different centrality bins, with more particles belonging to more central events. So basically this is how this is done experimentally to extract centrality. And then there's another thing, the reaction plane. In the initial state, we have this two colliding nuclei. So starting up here, and over time, as time progresses, that's where you see that this initial spatial anisotropy gets transferred into momentum space. So you see that there's basically strong pressure gradients in plane. So, and this really coincides with particle production in plane. You can see that in this basically this as you neutral distribution of charged particles from the star collaboration, you see different centrality bands that you see more particles produced in plane than we do out of plane. Okay, so now I will talk about the sPHENIX. This is basically a clip off of the 2050 long-range plan, which basically discusses the two frontier of physics, or basically two goals of things that one would want to close at RHIC before the EIC, one of which is basically mapping the QCD phase diagram. And this is really more of star-focused quest. And the other is basically probing the inner workings of the QGP, and sPHENIX is under construction just for that. Okay, now sPHENIX core physics program. So we're going to basically probe the QGP with different in different ways. So there's, we can establish jet correlations and look at jet structure. And so basically you can vary the PT and the angular size. You can look into Quark-Gluon spectroscopy, basically looking at the different upsilon states and seeing how basically seeing their suppression. You can also look into photon energy loss, and we also have a QCD called QCD program, small but growing. Okay. Now the sPHENIX detector. So this is basically a schematic of the detectors that are in place in sPHENIX. So first you have the SCPD. So this is more the detector that would do give us the event plane and also do some event characterization like some calculus and stuff like that. There's the MBD, which is also labeled here as well. So they're on two ends. It's also called the minimum bias detector. There's the inner HCal, and then there's the EMCal. In between the inner HCal and the outer HCal, there's a magnet, basically also drawn here. And for the inner tracking, we have a TPC, which is basically the cylinder. And inside we have the MVTX, and then there's also inside of the on the outside of the MVTX is the INTT, and then the MVTX is the most innermost detector. Okay, so the when the acceptance here really coincides with the central barrel, the inner detector, but we do have detectors that are beyond that acceptance. For example, the MBD and the EPD. So it's makes has high data rate, which is 50 kilohertz, and so it's triggered readout for the calorimeters, but it's triggered readout for the tracking physics. Okay, so let's look into the subsystem one by one. So for starting, we have the MVTX. So MVTX is basically a copy of the ITS2 tracker. So basically, it's made out of so it's called the map character detector. Basically, this is what's going to give us vertex and enable us to do some of our heavy flavor measurements. So it's nearest to the collision point, has a spatial resolution of 5 microns. And it has for tracks with PT greater than 1 GeV. Next, we have the INTT. For actually, if we just go back for a second, so this picture is from just yesterday. I'll talk a little bit more about it as we go along. But before the detectors are put into sPHENIX, they're sort of assembled privately in the lab in different rooms. And so this is from yesterday, where you have basically 2 halves of the MVTX. So this is an example of a half sector. And when you put them together, you have this picture. So this is something where we're basically trying to align them before they can be installed into sPHENIX. Next, we have the INTT. So this is also at Brookhaven National Lab. This will give us, information about pileup event separation. So it's a silicon strip detector. Basically associated with reconstructed tracks will be event that produce them. So this is going to be really good for pileup event separation. And then the TPC is really our main tracking detector. So it's smaller than the Alice detector. For those who work with Alice, this will provide our momentum measurements. Initially this was neons, but with the issue with getting them, so this is now the new gas mixture for the TPC, and this is basically a photo of it being installed about a month ago. So in sPHENIX, so this is the TPC itself. So it's gem-based readouts, just like the upgraded our TPC, and has a spatial resolution of less than 200 microns. Next, we have something called the teapot. It's basically the TPC asset tracker. So this is basically the teapot. It sits below the TPC. So this just gives us an extra way of calibrating our tracks. So this will, basically correct for beam-induced space charge distortions of the TPC. So it's micromega space, and there are 8 sectors. And it is, like I said, on the bottom half of the PVC. So this is basically the full tracking for sPHENIX. So like I sort of talked about initially, we have the MVGX, which is the most innermost detector, and this is starting from collision point all the way outwards. And so with this collection of detectors, we can we'll be able to get the measurements that we want. So so here I've just sort of highlighted, the MVGX higher resolution and without grid. Those are larger acceptance rules compared to other RHIC detectors, will allow us to get a hold of the state-of-the-art open heavy cleaver program at RHIC. So next, I move outwards a little bit and talk about the calorimeter system. So we have a hadronic calorimeter, and there are two of them, which is the outer cal and the inner cal. And so they're called OH-cal and IH-cal for short. Basically, they're plastic insulated. They're made of plastic insulated tiles, and they're tilted. So in between those plastic insulated tiles, there is steel in case of the outer cal, and then aluminum in case of the inner cal. And those insulating tiles are embedded with wavelength shifting fibers. So the segmentation for the inner and outer cal in 8 and 5.1, 5.1. So we also have the EM cal, the electromagnetic calorimeter, it's made of scintillating fibers, tungsten and epoxy. So it's of course of the segmentation of the hadronic calorimeter, so it's finer, has pretty good resolution. So here I should show you a photo of the installation process. So this is, you can see the inner cal being inserted. This is the magnet, and this is the outer cal. So it's being inserted into the inner cal some months back. Okay, so I talked about it needed to do open heavy cleaver measurements and jet measurements. So the tracking does a good job for the air cleaver, and then also the calorimeters will be allow us to do a jet measurements, especially with their hadronic calorimeters. Now then, a little bit further outwards is the sPHENIX as the sPHENIX event plane detector, and also the minimum bias detector. So I sort of talked about it a little bit in previous slides, but basically the MPD is we have two of them, and it covers this much in a sentence, and it's really a reuse of the sPHENIX BBC. Has 128 channels, made of 3 centimeter thick quartz radiator and mesh, and has a 120 picoseconds timer resolution. So, and then on the event plane detector, so this where the wheels on the very end of sPHENIX. So in this particular case, this is sort of the light green on this event display. So this is I sort of put a title test event display, but because this is not official in terms of what we're going to show and public in a large conference. However, this is basically the setup for our event display. We have a TPC, and these are different colors are the energy deposits from the EM cal, the inner cal and outer cal, and we can see the EPD on the very ends. So the EPD, we're going to use it for event plane. So we would like to get event plane and do some event plane dependent measurements. There are 2 wheels, 12 sectors. So the sectors are basically in 5. So it's not very hard and easy to see here, but they're basically segmentations in 5. And this is the acceptance is this much. It's between 2 and 4.9. There are 1.2 centimeter thick plastic insulators with embedded with wavelength shifting fibers, and there are 744 channels. Okay, so sPHENIX run plan. So we anticipate our first data in May 2023. So it's a 3-year run plan. As of now, I don't know the future, but this is what's in paper. We start this year with gold. This year, this one really will be for conditioning. We don't think we're gonna do any real physics just yet, but basically focus on commissioning and understanding our detector. And then in 2024, we'll do basically collect reference data sets. So we'll do PT and P gold. And then lastly in 2025, we'll collect our very large global data set, which in the combination will be about 1.1 billion events in total between year 1 and year 3. Okay, so now I go into projections. So I talked about our science mission, our detector, what it's capable of, and so now I'm going to talk about our projections and what we think we're going to have with the amount of data we collect. So here I show basically two different photos. One is just yields. So yields of, in PP versus gold, so heavy ions versus PP, and then in jets and direct photons and charged hadrons. And also you can look at the corresponding RIA statistical projections. You can see that the different reaches. So if you look here, if you see that you reach about 70 GeV for jets and 50 GeV for photons, and also this allows for implicit jet RIA and photon jet substructure measurements and so forth. And the key thing to note is that most of our measurements we do because the good thing about them is that they overlap with LHC measurements. So we're the lower end and the LHC are higher end, but the overlap region is also good so that we can better understand our observables. So now I show the projections for photon jet correlations. So here's as soon as on the left is their sPHENIX projection. Here is measurements from Atlas, which shows different separations for the Quark jet fraction. So higher, we know that there are higher Quark fraction in phototag jets than inclusive jets. So because of this, we can study further dependence of energy loss. As you know, the photon will never interact with the QGV, so this constrains the initial jet PT. So our projections of exponents of PT imbalance at lower PT extends the thematic bridge for Atlas, which starts at 79.6 GeV. So here we're going to be greater than 30 GeV here. Okay, so I talked about event plane. So apart from jet correlations with photons, we can also do correlations with event plane. So here is a distribution of particles as a function of with respect to the reaction plane. So the estimator distribution with respect to the reaction plane, and and similarly, we can also you see the projections from sPHENIX, and if you look here on the red, this is what we projected for our kinematic bridge and the statistics that will enable us to reach this point. And you see that this is a good overlap with measurements from Atlas and Alice. So the LHC measurements, so this would be good in terms of gauge measurements help us understand the behavior better. Okay, we can also do jet substructure with our high data amount of data. So jet substructure basically gives us information about the evolution of the quantum shower. You can see that in this will be the measurements from Alice. There you see that there's no modification in PP, which compared to lead. So and of course it also shows that remember the model predictions. And so this is also our projection from sPHENIX. We think that with the high statistics for 3 years of data really would allow us to extend the measurements at lower PT. And then also we can look into heavy flavor jets. Which are high data rate and high precision of the sPHENIX detectors. You can see that we can also do B-jet measurements. So you can see that in Atlas, for example, that going the wrong way. You can see that that in Atlas that the B jets at 0 to 20% centrality are less suppressed than inclusive jets. So also we can do that in the sPHENIX where we can push it down to lower BP, and this will basically allow us to study basically mass dependent jet suppression. So it's also we can look into ZG basically. So if you look, this is the B jet, and you can also look at substructure of this, and if you do that, then you're looking at the mass dependence of the quantum shower evolution, which also is possible in sPHENIX. Also, this is a measurement that was familiar to people in the room. So this is a measurement from Alice, basically showing the ratio of RA from with Alice for here, and then in Atlas on the right. And you can see that in the two different cases, there are two conclusions. One is that in Alice, I mean, there are of course caveats, but at first we can see that Alice reports that jets are more, so the large R jets are more suppressed, and Atlas reports that they're less suppressed. So students will also be able to do this measurements here at this region. So if you see the two results, we can see basically try to reduce the tension between those two results. Okay, and then so I talked about jets a lot, and so we're going to measure jets, and we're also going to do open and flavor measurements. So here I show the RAA of B methods. So you have so you have B to D and also from D0. So the high precision data rate basically allows us to study mass dependent energy loss. And also we can do a full behavior reconstruction. And so on the right plot is the B2, and you can see that we can also achieve this measurement as well. And then upsilon spectroscopy. The upsilon states will also be measurable at sPHENIX. So here on this left is these are sPHENIX projections for the different 1s and 2 states in black and in red, and then also and then on the right is just basically the data point itself in the array of it. And then here is just this is a simulation that we did, and we see that you can recover the 3S state. So anyway, we see that there are clear separation of upsilon states, which will allow for comparison between RHIC and LHC measurements. So this will be also be achievable in sPHENIX. And then lastly, we can also do we also have a pulse QCD program, so we would also do some observables related to pulse QCD. One of which is the photon and D0 spin symmetries. And so yeah, actually the spin symmetries for different so this is sPHENIX projection, and then also there's also a projection using as different from D0 to the 0 bar, and we think that there will be different behaviors when you compare the D0 to D0 bar. So this should be good also. So now I talk about construction status. Where are we? So So we started off with having the cradle base, move to BNL, and we started to put in the inner H-style sectors. So the cylinder, other H-style were actual individual sectors that were sort of put together. And then we mounted the magnets, and eventually then we put in the inner H-style rings, and basically for support, and then the whole other H-style sector was completed. And I showed you a photo some slides back where the inner H-style was inserted into the magnets, and then here I show basically these are EM cal sectors inserted into the inner H-style, it was passed here, and this is a basic creation of tool tips and carriage and things on the platforms, and then at some point it's moved to the interaction region. So it was once accessible to everyone, but now then it got moved to the interaction region, and then there was some testing with the magnet to make sure that we get the full response from the magnet of 1.4 Tesla, and then we put the TBC in like a few weeks back, and the INTC supports were also put in around the same time, and just a few days ago we put in the beam pipe. And then now we're working on the individual tracking detectors. So the INTC is in a room at BNL where they're doing the assembly for the whole, and then also the MTX as well. And so these are the two hubs which I showed were being put together to get a good alignment before then they'll be secured into the pipe, and then we do the MBD, and well, at the time this was done, we didn't have the EPD because EPD was acquired later on. It's an NFS MRI project, so it was basically gotten outside of the MIE detector, so to speak. So after the MBD, then we'll put in the EPD. So we're here, and so this is a photo of the beam pipe. Most recent photo of the beam pipe in sPHENIX centers with the TPC. Okay, so before I close the talk, I just wanted to share the collaboration. So this is a photo from a visit from January from DOE executives, and you can see sPHENIX behind here, and this is just a subset of some of the members of sPHENIX collaboration. So we're about 400 members, and several institutions and several countries and 4 continents, so now I go to my summary. So I hope I pressed upon you that sPHENIX will do key measurements of jets and heavy-vapor observables. It is the first detector I've put for over 20 years now, and it's a key detector required to complete RHIC size mission for 2023 through 2025. It has more improved precision because of all the new detectors that we have. And this will be our first measurements of the jets and upsilon 3s suppression at RHIC. And in most cases, we saw that there will be good kinematic overlap with LHD measurements. And as far as detector installation goes, we've installed the calorimeters inside the magnet. The TBC has been installed as well, and also the beam pipe. And then eventually all the other tracking detectors and APD and NPD will be installed in the coming months. And we look forward to an exciting physics program. Thank you, and now the questions.
All right, thank you, Ejiro, for a very nice talk and a very good overview of the sPHENIX. We have time for questions. So if anybody would like to ask any questions, please do so, and I'll
First, we'll do people in the room and then we can chat with people on Zoom. Join.
Yeah, I mean, first of all, it's a tremendous accomplishment, and all those who worked on it, really focused in this short time. I really hope that, you get the time and ensure it's out in your limited time.
Yeah. And especially during COVID, it was not easy, doing all that.
Yeah. Isaac?
Do you like this slide? 17? Actually, sorry, one more thing.
Yeah, my bad.
Yeah, could you explain a little bit more about the teapot? I wasn't exactly
Oh,
sure.
yeah, okay, so I'm not a teapots expert, but I can just give you a brief summary. So it's basically
Maybe I know the bit.
yeah, yeah, what? What's the question?
Because I was involved.
Oh,
Thank you. Okay.
okay, but so was it a direct question about the teapot or just
I'm just not exactly sure, what its purpose is in addition to the.
oh, okay.
Yeah.
So so if you see like the teapot is gonna be like basically giving you basically one extra point for the tracking.
Mhm.
So I mean, you know, so it wasn't part of the MIE, as you said, didn't talk about it in that construction status, but it was later acquired because we think that this will improve our tracking.
Because of the gems, I guess, no?
Yeah, and yeah,
It's to correct for the gem, the space
Yeah,
distortion?
yeah.
Okay, it's pretty neat.
Erika, can you keep this slide for the moment? Because I have my
Yeah.
question
Yeah.
exactly. I don't know, you can answer this one. Because
you got me pretty, but teapot's not my expert.
it's not gem based, not.
No,
No?
the TP is not gem based. The
Micrometric.
TPC is gem based.
No, micromegas
Yeah, yeah.
And really strip it out and two chambers one on top of another, one mirror deeper than another, one profile. So this is very crucial moment, by the way. So it's detailed that I will explain all that.
But I mean, as she said, sorry, as she said, it was put in after the initial detector was approved to make sure that you correct for distortions, because you don't get the distortions compared to TPC where you do.
Yeah.
Okay. Sorry, a lot of experience from previous experiments, that's now separated. First question, during installation, of course, you have to do any kind of optical alignment. Do you know
Yeah.
precision
Up to the, yeah, for the teapot?
for all chambers really, but really for default also crucial.
No, I don't know. I'm not involved with
Because
with tracking the
just
factors.
next question for any kind of alignment,
Yeah,
it's the first step. So use
Yeah.
what else optical can be done, and it's not a simple step.
yeah,
And second point, of course, for alignment and tracking detectors, you have to spend a lot of time with cosmic, for example, the zero field and so on, so on.
uh-huh.
Like an example, Alice just now, after all the improvement, everything,
Yeah.
is 5 months on a cosmic.
5 months on
Yes,
cosmic
yes.
for
Is any
commission?
such time on your schedule?
No,
Sorry, I don't know how you will struggle with alignment.
no, I mean, yeah, I mean, so we start, sort of a dry, because like RHIC will start like, in April. So around that time, from between April to May, we'll do
So in this
measurement.
case, precision
Basically
5 microns you mentioned for the third detector is indifferent. Because with such, I would say, high precision detector alignment should be done at least maybe after 2 bends. So with statistics should be, I don't know, what is 100,000.
But they are starting off with very low luminosity night.
Yes, we are starting with very
I
low
would
luminosity
totally
running
double
commissioning,
check.
yes, yeah, yes,
Yes,
yeah,
absolutely, this is very crucial moment.
Get rid of a lot of the distortion.
yeah,
Yes,
yeah.
because second point, 15 kilohertz have been fixed because really the simulation demonstrated this neon gas in a TPC. Phase change distortion can be done on the level few hundred microns. Okay. I don't know, 200 microns comes from before or after correction. It's very, very peculiar state. And after you come to argon, all distortions, at least factor 3 up. So what is the next step? Or just all your corrections will be done much better than before, or you have to reduce your rate.
Yeah,
It's only one way. So
Yeah.
if you all statistically presented for 15 kilohertz, think about it. It's also if we factor 3 down, for example.
Yeah.
3 times more time.
yeah.
So this is very unpleasant state when the people found that neon is not available.
Yeah,
Unfortunately.
yeah, yeah,
Okay, but I have a lot of technical questions after this.
yeah. Yes, yes.
It's probably best, just why have both an inner and outer H file?
Okay, why that? So the inner shell is between. So the inner shell is between the magnets. So you have the inner shell inside the magnet and outer shell outside the magnet. So we think that the combination of the two will get us full jet measurements. So basically, since we want to do jet measurements, the combination of the two will give us the jet measurements.
Magnet came first. That's
Yeah, from slack, magnet came first, yes.
I hope that
and they
you,
need a certain depth, right?
Yeah.
So.
Which magnet is this? The bar magnet?
Yes, it's the development.
The bar magnet?
And Katie?
Yeah, I have, I guess, 2 questions. The first is about the teapot. So you can say something about a lot of it here, but I guess I don't understand. It's outside of the TPC, how it's supposed to correct for distortion. Because if it's outside of the TPC, then I mean, aren't the tracks like already distorted by the time they get there?
Because if you look at this, like imagine you have a point that is now they need a
Yeah, it's
better
it's a freaking pointer, I'm sorry.
So I mean, if you have a point outside and you have distortions here, I mean, the point that is like independent of this it has to be outside for you to basically just figure out what is
let me
what the
comment,
point should be.
because really, phase jet distortion correction is extremely complicated
Yeah.
step. And it's minimum 2 steps to be done.
Yeah.
First, what was mentioned was missed completely readout. It was never mentioned what kind of readout, what kind of data will be, what a step in your report.
Yeah.
It's step separate problem. And first step is during readout, very fast online, you can do first step correction using some model and using data from LiDAR, what is available,
Yeah,
particularly for this one. And then, if you can do this one, then you try to match your track after first step correction. This heat outside.
Yeah.
First of all, it's separated you from different vertex positions because timing is different. Of course, you
Right.
have drift time. It's reasonably long. This is fast time. It's exactly.
okay.
You
Yeah,
selected
yeah,
first
okay.
of all what kind of vertex you have to use, particular for the event. It's
Okay.
first point.
Yeah.
And second point, then your second correction, exactly matching. But you can also realize that teapot is only a few chambers. It's not covered all.
Yeah. So
What does it mean? It means you doing average correction. You're going for few tracks,
Yeah.
correction, and then think that absolutely the same for all.
Yes.
It's an additional distortion.
Okay.
So it's really very complicated.
I
Yeah,
think what I was
this is-
missing, yeah, oh, sorry.
No, I was just gonna say that was all the money we had.
Been misunderstood was
Yeah.
that I sort of thought the teapot was like on the end caps with. the-
No,
like,
it's,
I thought the readout was
no,
on the end.
No, it's right underneath, like right here. it
Yeah,
says
okay,
here.
and then you can match.
Yeah.
Okay, that
One
makes
from outside.
more sense, okay. And then my second question is more of a physics question. So
Yeah.
you mentioned a lot of the sort of measurements that sPHENIX will be able to do
Yeah.
and compare to like the LHC, which is really
Yeah.
cool.
Yeah.
But is there anything that you're really excited for that like LHC, not LHC, sPHENIX can do uniquely that like we haven't been able to do at the LHC or at STAR that?
I think it's really that sPHENIX will do measurements in RHIC. For example, the B jets, for example, so this is like RHIC specific, and then also we extend the kinematic range.
Okay.
Yeah. But for me in particular, I'm more excited about the JetV2, which will be one of the first measurements coming out of the sPHENIX. So we'll see how that goes.
I also like that.
Yeah.
I have a little question, I guess in slide 24, I'm just curious about this temperature that is used in the plot. I guess it's the next one?
24? Oh, sorry.
Yeah. There's a temperature somewhere. 27, sorry.
Oh,
Oh my God, okay, no, I wrote the wrong thing. Well, anyway, so let's just move on, like, with respect to like the upsilon productions, I guess like further on, you have the, here, yeah, so I guess out of the 24 billion events, I mean, we have this in the binning about like 1,600, I'm like, we really expect to measure that many? Because this thing is super massive, right?
What?
The upsilon one is?
Okay, so do we expect to like measure the upsilon, you're saying,
Like,
and the different states?
yeah, I guess like how many do you think we expect to see in like a highly central collision?
Okay, well, I will not be the best person to give you an answer on that because I'm not a Quark-Gluon person, but I mean, my guess is, I mean, is that you, of course, you're gonna see more of the 1s, the 3s is, you know, very small, as you can see, physically on this count here, and we might not even see it, it might be barely visible in gold, so, I mean, we don't know, we're just speculating that we might see a 3s statement.
Because one state is well measured, I think.
Yeah.
Right, so
Yeah.
at that point, well calibrated, assuming the efficiency is done. So I think
Yeah.
the big peak is the key thing is that
Yeah.
you just said,
Yeah.
right, that you
Yeah.
can get
Yeah.
only
What
the
is-
3S state.
Yeah, hopefully, yeah.
And
I'm
then
not sure
it's
yet, but
peaking.
yeah.
So
Yeah, but
that
that's,
one big peak is pretty well.
yeah, that's a pretty
Yeah.
interesting measurement too.
Otherwise, yeah.
But once more, such comparison can be done only in the case if in proton and then gold, you'll do the same value. In this case, yes, you can get that. But for example, phase change distortion doesn't allow you to get the same nice peak like this.
Mm.
It will be another story. So only real experiments will demonstrate.
Yeah, this is simulation without
Simulation.
the effect of the tracking and distortions. So, yeah, we'll see what happens.
So am I remembering correctly that that the first run is a gold run, like for the first whole year? Is that, did I miss this?
Yeah, it's all over.
Gold first, right? No PP
Oh.
yet, right? Like you'll have
No.
a full data set of gold.
The
Before
third
you-
year. Oh,
before you
okay.
have-
So, yeah. So, yeah,
That's the condition.
Yes, it's commission.
so this is commissioning of year.
That's why they sort of have 9 weeks of physics, but the rest of it's 24 weeks.
Yeah.
Commissioning.
So you will have proton before you take the gold, or you'll have gold, like, I guess, sorry, my question is will you have yeah, that's the answer, the first physics method from gold. So if you'll have first physics will be from gold,
Yeah,
right?
Yeah.
So I guess what my question was gonna be is, I guess, what measurements are you most excited about from that first? Is there any others that you're excited
Because it will
about?
take-
Given that gold, given that the first year will be gold, but no.
Yeah, so there's a reason why I said the two, because you don't have to do like, so much of the corrections and things like that. And there's also the, digest analysis to, one could do digests as well. Yeah, this is what we think will come out of this for next the first year, this digest and JetV2. Yeah, I mean, for more complicated stuff, we need to really understand the detector more before we do.
Some optimistic guys from this night collaboration told me open that for first year we don't need any tracking. We will use only calorimetry.
Right.
What do you do
So-
with digest in the one?
The what?
What do you do with digest without a calculator?
Well, you don't have to do RIA, you can just, I don't know, just look at the PT imbalance or something like that,
But you have to know what the imbalance is.
you have to know what?
You can figure it out later, no?
Well, I mean, you need a PP and an AA to come through.
Yeah, that's right.
Yeah,
Maybe follow-up, can you do photon jet in your one? Is that projected for your one?
Photon jets, I mean, I don't think you have enough well, it's gonna be for condition and low luminosity, and then you need a lot of statistics for photon jets, so, yeah.
How good is your soft sector?
Bulk,
Yeah.
it's growing, so. Yeah, and, you know, one of the few people growing it, since I really come from a bulk, background, so I mean, you know, we think we're gonna do, you know, of course, I showed some, projections for V2. Jet V2, it's sort of a combination of the two. You really need the event plane, and, you know, and then, you know, the jet from jet group. There were some people who wanted to do balance functions, so, I mean, so it's sort of growing, and we'll see, what actually comes out of the bulk group, but it's not, of course, sPHENIX main physics core, program, but there are some measurements that will come out of it. We'll see. Yes.
Can you go to slide 27?
Yes. This one?
Next one.
Oh, 27.
So I guess when you compare B meson to prompt B0, in addition to how much they are suppressed as compared to like unity, are the peaks supposed to tell you something in addition as well? The left. Oh,
The
I was
left.
looking at
The left one. Yeah.
Yeah,
So you mean the peaks where the peaks are starting? Or,
yeah.
well, I mean, so this is a function of PT, so I mean, so there is probably a PT dependence there with the RA.
I mean, so
So-
far, everyone sees
Yeah.
the RA moves out with mass more or less, right? The
Yeah.
protons are peaked out farther, you know, than ions, for example.
Okay, but then there's a pion peak almost the same point as the D0 peak. Like,
Yeah, I see what you're saying, like, it's around the same point as the zero.
yeah, so like it couldn't just be mass or flavor.
But this isn't data.
Yeah, exactly.
Yeah.
It's
question,
it's
what's
just a
the
projection of, you know, based on our, you know, the amount of data we're gonna get, and it's just really placing the points, and I think what's most important to focus on is the error bars on the data points, which is really just the, you know, you're looking at the given our statistics, how far we can go in this condition.
So I guess in addition to the parton like mass, it's like parton mass and flavor dependence. That's what this
Yeah.
measurement is going on.
Yeah.
Okay.
Is sPHENIX considering doing low mass leptons? I mean, there's high statistics. It's a question of whether you get the, you know, what you can do down at low mass.
Yeah. So I don't really pop in the Quark-Gluon group so much, but it's not in our being used proposal, it's not what we just talk about. So you could base on it.
Alan, do you know whether they might be competitive with STAR? And low mass leptons?
I don't know how magnetic field.
1.4 Tesla.
That might be some. Just reconstructing low enough.
Well, they're more compact, but I don't know, yeah. That's true. And then all of your simulations are 1-3 years. And the
Yes.
first year is
Yeah.
probably not going to contribute to that. And the
Yeah.
second year is protons.
Yeah.
So is that? Well, okay, you put the integral luminosity, so I guess.
Yeah.
I could see.
I guess maybe John's question phrased another way is like, for these simulations, were you assuming that you had a long run in year one?
Yeah,
But that's not quite shorter.
yeah.
It seems that's the case, I don't know.
I don't know,
The
they
goal-
might have to
Long year, never-
multiply by factor two, is it over five?
Oh,
You know, sort of like, I don't remember what. I mean,
Yes,
people always
yes,
do have
yes,
information in year one.
right, right,
So
of course, yeah,
how would
Yeah.
they data in year one of the?
yeah,
Yeah.
yeah, so these plots come from, earlier in the year when we had, high hopes and thinking we can do everything, but as we get closer, I think some of these plots might need to be redone, given that the fact that we, we're really gonna spend a lot of time commissioning rather than, taking real, luminosity inputs of data.
It's cute.
Yeah, so in, I guess year two, this would be your first photon year. Are there any plans for a jet B2 and P3? Anybody knows?
Jet B2 and PP. Yeah, so you're thinking of, there was this atlas measurements of high PT hadrons in, PLED, for example. You're just trying to see, basically asking to compare to that to see if there's
Yeah,
be a sizable V2 or something.
I just think it would be interesting. Well, I would be interested to see a V2 and PP, but I don't think we've done it, quite frankly, because it would, need to be done with two particle correlations, which
Yeah.
jet people tend to stay away from, as opposed to just pulling event planes.
Yeah.
But I'm wondering if sPHENIX have any, like, plans to do this, or?
No, I mean, of course, the option is there if someone wants to like knock your head at it, but the option, we're definitely getting the Jet V2, go first, yeah, that's the main focus, yeah.
Hey, no, I would do that with doing a jet hadron two particle correlation. I don't really have any.
Yeah, I think so.
NPA, yeah.
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 Do it like
Yeah.
any other
Yeah.
V2, except you just
Yeah.
do the jet as a.
Yeah, yeah.
Could you do just the jet one and then look at the PP? H jet PP, kind of quickly.
I mean, yeah, you need a well-defined thing to do it
Yeah.
that way, so I don't know, kind of simplicity, maybe I think the sketch. I think it should both. Two particle correlation, and two object correlation would probably be better, so. I mean, I'm trying. Throwing out ideas.
All right, so it seems like we're getting close to the end. If there aren't any more questions, then let's thank Ejiro one more time.
Anyone online?
Yeah, is there anybody online who maybe has a question? I don't think so. It might just be us. Yeah, I think it's just us. One participant. Yay!
Yeah.
Yeah, yeah.
Yeah.
All right, well, let's thank Ejiro once again.